This video is about the theorem of what we call the fundamental theorem of cyclic groups, and this will be the last theorem in this chapter. Every subgroup of a cyclic group is cyclic. So if you have a group G generated by A, so G is cyclic, and if you know that H is a subgroup of G, if G is cyclic, G is cyclic, G is cyclic, H, subgroup of G, is cyclic. Now, if the order of this group is n, so if the order of G is n, then the order of any subgroup, and this is a subgroup of the group generated by the generator A, is a divisor of n. So the order of H will divide n. And for each divisor k of n, so for each divisor k of n, for every single k that divides n, the group A has exactly one subgroup of order k, namely a to the power of nk, meaning so that for each divisor k of n, this group has a subgroup of order k. So there will be a subgroup I'll say what the power is here. So there will be a subgroup of this group A, okay, of this group A. There will be a subgroup, and the order of this subgroup, the order of this subgroup will be k, and the element that is going to generate this subgroup of order k is going to be the element n dividing k. And so it's pretty intuitive, pretty logical. The proof is not hard, but the proof is long. Okay, for the proof, we are going to take G as a group generated by A, so a cyclic group, and we are going to suppose that H is a subgroup of G. We want to show that H is cyclic. Okay, if H is only the only element in the set is the identity, well, then it's cyclic, proved. Okay, so let us take H different from the identity. So if H is different from the set with only the identity, since H is a subgroup of G and G is cyclic, H must have an element in the form a to the power of t, okay, with a positive t. So H must have an element a to the power of t, where t is positive, and H to the power a to the power of t will be in H for sure. Do not forget that the elements that are in H, they come in the form of powers of A, since G is cyclic. So every element in H will have this form, AT. Okay, and what about if a to the power of t is in H but t is negative? Well, then so that will be a to the power of minus t, but a to the power of minus t should be in H also, and so minus t should be positive, right? Okay, so H must have, that's our claim, H must have an element in the form a to the power of t. Okay, now we are going to pick a m, and m is going to be the least positive integer such that a to the power of m is in H. Okay, a to the power of m will generate a subgroup of H. Okay, but we say that H equals a to the power of m. Okay, and we have to prove this now. What we do is we take an element b, arbitrary in H, and we have to show that b is here. B is in the set generated by a to the power of m. Okay, b will be in G, right? And b and G will be generated by a. So we have b will be equal to a performed k times, okay, for some k. Now we have to apply here the division algorithm to k, and to m, okay, to obtain the usual integers q and r. Okay, so we are searching for k equals mq plus r, of course under the usual conditions where r is positive and also m is to be greater than r. Okay, so what is a to the power of k? A to the power of k is this, right? So it's a to the power of mq plus r, which is equal to a to the power of mq times a to the power of r. So okay, I'll make this the subject. A to the power of r will be equal to a to the power of minus k, yes, this one here, minus, and this one will be a to the power of k, right? Okay, but we said that a to the power of k, where is it? Here. A to the power of k is b and is in H, right? So a to the power of minus mq will be equal to a to the power of m minus q, the inverse of m, and this one will be in H, right? So a to the power of r is in H2. What did we say about M? We said M was the least positive integer, such that a to the power of m is in H. And do not forget also these conditions here, okay? M is greater than R and is positive. Okay, so here R has to be 0. Okay, so a to the power of minus mq ak has to be the identity. Okay, so b will be where is my b? I lost my b now. I might, yes, b is here. B will be equal to a to the power of k, and a to the power of k, as we saw, has to be a to the power of mq, since we proved that this r has to be 0, right? This r this r here is 0, so b is a to the power of k, a to the power of k is a to the power of mq, a is to the power of mq. So this is a to the power of m power q, and this is in a, in the set generated by the powers of a. So this proves that every subgroup of a cyclic group is cyclic. Okay. So now I want to prove that the order of H is a divisor of the order of A to the power of M, right? Every subgroup of a cyclic group is cyclic, proved. If the order of A is n, then the order of any subgroup of the group generated by A is a divisor of n. So that's what we want to prove. We want to prove that the order of H, subgroup of G, is a divisor of the group generated by the powers of m. Okay, so let us pick the group A and say that its order is n. And let us say that H is a subgroup of A. Okay. Above we showed that H equals is generated by m powers of A, okay, for some m. Okay, and since A to the power of m performed again equals a to the power of n m, this means that E, the identity to the power of m, equals the identity. Okay? Now, I'm going to use the corollary of the other theorem, where we said that a to the power of k equals the identity, implies that A divides K. Okay, I'm going just to remind you. Let G be a group and A an element of G, and this element will be of order n. If A to the power of K is the identity, then n divides K, and the proof was really simple. Okay, because the proof was really simple. We just said if A to the power of K equals the identity, that will be equal to the power of 0. Okay, and by the theorem we just used, it was the criteria to A to the power of I to be A to the power of J, right? So so n here divides K minus 0. Well, that is, n divides K is the same as saying this. So I'm going to use now this corollary. Okay, A to the power of K equals the identity implies that the order of A divides K. So by the corollary used above, A to the power of m, the order of A to the power of m should be a divisor of n. So the order of H equals the order of A to the power of m. Okay, so it is a divisor of n. Now we are going to prove this, and so it just proved that if the order of A equals n, then the order of any subgroup of A, of the group generated by the element A, is a divisor of n. We just proved that. Now we are going to prove this here. For each divisor K of n, the group generated by A has exactly one subgroup of order K, and that subgroup will be A. It will be the group generated by A to the power of n dividing K. Okay, let K be a divisor of n, and we are going to take T as n dividing K. So what is A to the power of T to the power of K? It will be A, so T is n dividing K. Okay, a very convenient T to the power of K, and that K, so that will be the identity. And A to the power of T, I go back to T, to the power of S will be the identity. Of course, S has to be smaller than T, so because A to the power of T, the order of this should be K, right? The order here should be K. I don't know if let me redo it. So S has to be minor than T, and A to the power of T, right? the group generated by a to the power of t, this t here, has order, the order is k, okay? Okay, now we have, I want to get to the conclusion that a to the power of t, the group generated by a to the power of t, is the only subgroup, is the only subgroup of order k. We already proved that there is one, but we have to prove that it's the only one, okay? So let us think of H as a subgroup with order K. Okay, we already showed that H is generated by a to the power of m, right? Where m is the least positive integer such that a to the power of m is in H. We saw that, and now we do the same. N to the power of n equals mq plus r, positive numbers. So the identity equals a to the power of n equals a to the power of mq plus r equals a to the power of mq times a to the power of r. So I'm doing this fast because this is more or less what I've done. mq, and then I exchange here, right? So a to the power of m, I put it to the power of minus q, and this of course is in the form of the elements generated of the subgroup H. Okay, so we proved again that R has to be 0 and N has to be MQ. Okay, so K will be the order of H. That will be the order of the group generated by a to the power of m. That will be, if you remember well, K, so it will be N divided by M, and that will be Q, right? So M equals, let me see, M comes here, Q comes here, right? So M equals N dividing Q, so that is N dividing K, right? N dividing K equals this one. N dividing K equals T. Okay? So this proves that H, the subgroup, is generated. H is the subgroup generated by powers M of A. Okay? Or A to the power of T. Okay? And that concludes the theorem. That concludes I keep saying this, that concludes the theorem, that concludes the proof. Well, several proofs, actually 3 proofs here.